Okay, so we're going to go into our next kind of convergence tests, which are two different types of comparison tests. So the first one that we're going to look at is the direct comparison test. So this is a little bit like the squeeze theorem, where we take something that we know about and we compare it to something that we don't know, and that's what we're trying to figure out is like the answer to that part. And based on what we know about the other one, if it meets certain requirements, we can determine things about the unknown one, which sounds really confusing, but we're gonna go through it. So you have two conditions that you have to have. You have to have two different sequences that are both positive or equal to 0. So if we have a sequence AN that's greater than or equal to 0, and a sequence BN that's greater than or equal to two things. If the series from 1 to infinity of B of n converges, and B of n is greater than or equal to A of n, then the infinite series from 1 to infinity of AN also converges. So breaking that down, that means if you take a series that converges and it's bigger than another series that you're not sure about, the smaller series has to converge. Whereas we can also say the opposite. If the series of A of n diverges and A of n is less than or equal to B of n, then the series for B of n also diverges. So basically, if you have these two sequences and you can put them in order, you can say that one of them is always greater than or equal to the other one. If you know that the smaller one diverges, then the bigger one is also going to diverge. But if you know that the bigger one converges, then the smaller one will also converge. So the tricky part is you usually have to come up with the second series that you're going to compare it to. And you want to always take note that you absolutely must state the inequality. When you state the conclusion of the test. So when you are justifying your convergence or divergence statement using a direct comparison test, you have to state the inequality. You have to show that you know which one is bigger or smaller than the other one, and because it converges or diverges, that's why the other one is bigger. Okay, so we're going to do a couple examples with the direct comparison test. So, and we're also going to justify all of these statements. Always, right? Practice our justifying. So just like before, right, whenever you are asked to determine if a series converges or diverges, the first thing you always want to do is do the nth term test. So we always want to take the limit as n goes to infinity of the sequence that's on the inside. Right, so here I have a rational function that has equal degrees in the numerator and denominator, so my limit's going to be 1, and so that does not equal 0. So this is actually going to diverge by the nth term test. Right, so you always want to start there because you don't want to have to go through and do all of this work, especially because with the comparison tests you have to come up with the second series, you have to state the inequality and make sure that you know that that's accurate, and then go through all that work. Whereas if you just start by taking the limit first, because a lot of time the limit's pretty fast to take, you can at least give yourself a jumping off point, especially if it's going to diverge anyway. Okay, so now we're going to take a similar series, but it's going to be a little simpler, right? Instead of having n cubed over n cubed plus 1, we just have 1 over n cubed plus 1. So just like before, we're going to keep in this habit, we're going to take the limit first. Right, so because the limit equals 0, this fails the nth term test. And when it fails the nth term test, that just tells you that you have to try something else. So we're going to, of course, do direct comparison because that's what this topic of notes is about. So we need to figure out what to compare this to. So the easiest thing to do when you compare is to kind of take the sequence on the inside and then just take the simplest stuff. So you kind of just ignore anything extra and look at the bare bones of the sequence. So the general building block of this sequence in here is 1 over n cubed. Okay, and this is great. And actually, I'm going to rewrite this as a series. So 1 over n cubed is a convergent p-series, right? Because 3 is greater than 1, right? Remember when the exponent in the denominator, when it's written like this is a p-series, and when that exponent in the denominator is bigger than 1, it converges for all n greater than or equal to 1. So all we have to do now is kind of show that the inequality that we want is true, and then we can use the direct comparison test. So we have a convergent series, which means that if we have a convergent series, we are looking at case 1, right? We want to show that this series is always bigger than the series that we are looking at, because if something that is bigger than the one that we're working with is always convergent, then it makes sense that the smaller one also has to converge. So one way to do this is we want 1 over n cubed plus 1 to be less than or equal to 1 over n cubed. So we can just manipulate this and see if it's a true statement. So I'm going to cross multiply here. So I'm going to get that n cubed is less than or equal to n cubed plus 1. And then if I subtract n cubed from both sides, get that 0 is less than or equal to 1, which is always a true statement. So because this is true, right, because of this work, we can say that 1 over n cubed plus 1 is always less than or equal for 1 over just n cubed, right, for all n greater than or equal to 1. If you're interested in doing this in like math symbol notation, for all n greater than or equal to 1 can also be written as an upside down capital A. That means for all n and then greater than or equal to 1. So because this statement is true, we can say therefore the infinite series from 1 to infinity of 1 over n cubed plus 1 converges by direct comparison to the series 1 to infinity of 1 over n cubed, since 1 over n cubed plus 1 is less than or equal to 1 over n cubed. So it's a little confusing to like know how to state everything. So you want your work to kind of show all of this. You want to definitely state what you're comparing it to and whether or not that's converging or diverging. Then you want to kind of show that your inequality statement is true, and then you want to put it all together into kind of a summary statement about whether or not the series you were asked about is converging or diverging. Okay, so let's do a few more examples. So again, we're going to start by taking the limit first. and so that goes to 0, so it fails the nth term test. Right, so the next thing that we need to do is find a series to compare it to. So again, we're going to say that we're just going to take out all of the extra stuff. So instead of having 1 over 3 to the n power plus 2 in the denominator, I'm going to take out that plus 2 and just compare it to this. But I can also rewrite this to be the fraction 1/3 all raised to the nth power. And now this is a geometric series because we have something being raised to an exponent, a variable exponent, and because 1/3 is less than 1, we have a convergent geometric series here, right? So which is a convergent geometric series. Wow, my spelling is awful today. Whew. Okay, we got this. Right, we can actually say what this converges to as well, but we don't actually have to do that. So remember, if we know a convergent series and we're comparing that to some unknown series, we want to show that the one that we know about, the convergent one, is bigger. So we want to show that 1 over 3 to the n plus 2 is less than or equal to 1 over 3 to the nth. Now, we should be able to just say that, which you totally can. You can say that this is always true, and if you had to justify it in words, you could say because they have the same numerator, but the denominator of the fraction on the left is always a bigger value, meaning the overall value of the fraction is smaller. You could explain it like that. You could also, again, cross multiply if you want to show it algebraically. Right, and since 0 is always less than or equal to 2, that's a true fact. So we can say that 1 over 3 to the n plus 2 is always less than or equal to 1 over 3 to the n for all n greater than or equal to 1. Sorry if you hear some noise in the background. We're doing laundry, so that's going on. So now all that we have to do is put together our little conclusion statement. Right, so I'm going to put my 3 dots for my therefore. The series from 1 to infinity of 1 over 3 to the n plus 2 converges by direct comparison. To our geometric series. And we could say since 1 over 3 to the n plus 2 is less than or equal to 1 over 3 to the n, and we could also, if we want to be super thorough, we could also say, and since 1 over 3 to the n is a convergent geometric series. Probably need to move some of this over because I just took up a lot of space for that answer, and that's okay. Just reorganizing myself so I have more room for the next problem. Okay. So our last one here, right, again, we're going to test the limit first. And that is going to equal 0, so it fails the nth term test. So I'm not even going to bother writing that out this time. So again, we're going to compare it to the simpler version of 1 over the square root of n, which we could also rewrite this as 1 over n to the 1/2 power. So then we can see that it's a p-series. And 1/2 is less than 1, so this is a divergent p-series. Okay, so this is our first example of doing a divergent series with the direct comparison test. So we want to show that for divergence that this is going to be like our A of n, right? This is basically where we're at here with example D. So we want to show that the sequence that we're comparing it to is actually always smaller than the problem that we're trying to figure out. So what we want to show is that the series that we just came up with is less than or equal to 1 over the sequence that we were given at the start. Which it makes sense that this would always be true, right? Because the square root of n minus 1 is smaller than the square root of n, always, which means that the value of the overall fraction is going to be bigger. But again, you can do it algebraically, right? Cross multiply. And then we get negative 1 is less than or equal to 0, which is always true. Right, so we can actually just go ahead straight to our conclusion statement. So we can say that the series from 1 to infinity of 1 over the square root of n minus 1 diverges by direct comparison to the series from 1 to infinity of 1 over the square root of n, which is a divergent p-series, since 1 over the square root of n is always less than or equal to 1 over the square root of n minus 1. Okay, I think I actually have 2 more examples of this on the next page, and I do. So we're going to go through those last 2 examples for direct comparison, and then the next video is going to cover limit comparison test, which I actually prefer to direct comparison, because you don't have the inequality business to deal with. Okay, so if we're looking at example E, right, cosine of n, so this value is just oscillating. Remember, this is called an oscillator. Right, it's just oscillating between 1 and negative 1. I guess you could say it in the other way. Right, so the value of the numerator is always just going between 1 and negative 1. So we always want to, of course, test the limit first. So because of the oscillator in the top, I'm going to test the limit of the absolute value. Right, and if I take the absolute value, that's really just going to take out the cosine in the numerator. So since the limit of the absolute value equals 0, the limit of the overall sequence is also going to equal 0. Remember that theorem, that absolute value theorem back from our sequences topic. Alright, so we fail the nth term test. So time to get down to comparison. So we're going to compare it to the series from 1 to infinity, right? Remember, we're just taking out like that extra nonsense. So the extra nonsense in this problem is actually the cosine in the numerator. So we're just going to compare it to 1 over 2 to the n, which is the same thing as the series from 1 to infinity of 1/2 to the n power. Right, and if we write it like that, now we can see that we have a geometric series. And because 1/2 is less than 1, right, this is a convergent geometric series. Okay, so now we just want to show that the cosine of n over 2n is always going to be less than or equal to 1 over 2n. And remember, if we have a convergent series, we want the series that we know, the convergent one, to be bigger than the one that we're testing for. Okay, sorry, I had to take a sip of my coffee. So, let's change this color so it just stands out a little bit more. Okay, if we cross multiply here, right, they have the same denominator, so what I can really say is that the cosine of n is less than or equal to 1, and that is always true, right? That's true for all n. Right, so I'm just going to tack that onto my little statement and then write my conclusion. So that means that the series from 1 to infinity of cosine of n over 2 to the n converges by direct comparison. Right to that guy, a convergent geometric series, since, we'll get a little squished on room here, cosine of n over 2 to the n is always less than or equal to 1 over 2 to the n. Right, there we go. Okay, one more example for direct comparison. If you want, actually, why don't we just go ahead and pause the video here. You try this one on your own and then unpause and check your answer. Okay, so notice that this one starts at 2 instead of at 1, and that's because if you plugged 1 in for n here, you would get 1 to the 4th is 1, and then 1 minus 10 is negative 9. And remember, for direct comparison purposes, you want all of your terms to be positive. So it starts at 2 because 2 to the 4th is going to be 16, and 16 minus 10 still gives us a positive value. So that's why it starts at 2 instead of at 1. So I'm still going to start my limit test, right, my nth term test, which we know right away it's going to fail because that's equal to 0. But I like to do this every time, even if you know it, and I like to write it out just because it gets me in the habit of always checking, so that way I don't overlook it. Okay, so we're going to compare the series that we want to know about to this series, which is just taking out all of the nonsense, so 1 over n to the 4th. Right, and if we know stuff about the series from 1 to infinity, we can make the same conclusions for 2 to the infinity. It'd be great because you're just taking off that first term. So this is a p-series, and because 4 is bigger than 1, it's a convergent p-series. Right, and I'm writing all this out because I think it's really good practice to always justify all of your steps and kind of write it out, because you want to understand what you're doing versus just going through the mechanics of what you think is going to happen. So remember, if we want to compare it to a convergent series, that convergent series that we already know about needs to be bigger than the one that we're trying to figure out. So we need to show that this is a true statement, right? So if I cross multiply here, I get n to the 4th is less than or equal to n to the 4th minus 10. So 0 is less than or equal to This is a weird turn of events. Okay, interesting. Actually, I'm a little curious about this, so let's look at the graphs here. Getting a little tripped up here, and that's okay, right? We can explore all of this together. I'm looking at my notes, and I have it written differently. Okay, so we want to know about 1 over x to the 4th. And we want to compare that to 1 divided by x raised to the 4th minus 10. Okay, and we really just want to go for x greater than or equal to 2. And then put that in here as well. Okay. Okay, so it looks like the one that we want to show about is actually not a great tool for this, right? Because if we look at it, scrolling out and out and out, or we could make a table on Desmos if we want, but we don't have to, right? Our blue line, which is the series that we want to know about, it looks like that sequence we want to know about actually is always bigger than the one that we know about. So we can't actually show what we want. Right, so this actually fails direct comparison.